All right, today we'll be talking about light and its relationship to electrons. As we've studied light, of course, Isaac Newton discovered that light was traveled in waves. He was able to take the prism and split the waves into the rainbow, and we've been able to do that for a long time. But there's been some discussion about whether light was a wave or a particle. Heisenberg had the uncertainty principle. Light behaves as both a wave and a particle. We can either know how fast it's moving or where it is, but not at the same time. All right, this drawing is a three-dimensional drawing of both the electric field and magnetic. In the electric field, you can see these are transverse waves, which are waves like ocean waves that go up and down. If you've ever taken a jump rope and made it go up and down. And then at a right angle to that, in a different plane, we have the magnetic field. And we can induce currents using a magnet. You can use a magnet and wrap a coil around the magnet, and just moving the magnet in and out of the coil, you can create electricity. Okay, so when we talk about light, we talk about the electromagnetic spectrum. All right, now let's see. I can do this. All right, so here's the electromagnetic spectrum. This is one of my favorite things to teach because I get to sing to you. The electromagnetic spectrum, when we talk about light, we're thinking just visible light, but there's actually much more light out there. There are bugs, fruit flies flying around. The entire spectrum consists of wavelengths that are up to 100 meters long, and those are radio wavelengths, all the way to gamma radiation, which is going to be, I couldn't tell you what unit that is. I'd have to stop and think about it. But teeny tiny. To give you a little bit better idea of size, radio waves are about the size of a football field. Microwaves are about 1 centimeter. When we're talking about light waves, it's in the nanometer range, which is 10 to the negative 9th it's in the 100 nanometer range, which is 10 to the negative 9th. So it's 3, 6, 9 times smaller than a meter. Ultraviolet rays, X-rays, and gamma rays are all extremely small. Now, stop and think about light. When I was a kid, we didn't know there was a hole in the ozone layer. So I used sunscreen with an SPF of 4. And up until, even college, because they discovered the hole in the late 70s, early 80s. Okay, why do I need sunscreen? Well, it's because ultraviolet radiation is so small it can get through the skin layers and disrupt cells. And we now know, of course, it causes cancer, causes melanoma, and that's why your parents have been putting sunscreen on you since you were a wee young thing, because our skin is just not created to keep the ultraviolet radiation out. That's what our ozone layer does. And good news, the ozone layer is making a comeback, so yay for that. Okay, X-rays. Stop and think about when you get X-rays. If you get to go to the dentist, they bring that big apron out and set it on you. If you go to get a leg X-ray, they may give you some kind of a shield to protect your reproductive organs because they're very sensitive. That's because X-ray is energetic enough to pass through soft tissue, but it doesn't go through bone. That's why X-rays, your bones show up as white. The light did not get through and get to the film behind it. Where it got through your body, it changes it dark, but if it didn't get through, it stays white. Gamma radiation, the last type of radiation we talk about, is released from the nucleus. We'll stop and think about how small a nucleus is. All right, so that's teeny tiny radiation, the size of a nucleus or smaller. Gamma radiation is associated with radioactivity. There was a show on this summer on HBO about Chernobyl. Chernobyl was a nuclear power plant in Russia that had a catastrophic failure and released a ton of radioactivity into the air. Interestingly enough, of course, the Russians told no one, and the world, the Western world, so to speak, discovered it when the Swedish nuclear plant workers were going into their nuclear plant and setting off radiation detectors going in. Those detectors are there to make sure they don't come out radioactive, and they were going in radioactive. So that's when the world finally found out. And it was a horrible, horrible accident. It could have been much worse. If you're into things like that, it's a really good series to watch. And there's a good book that goes with it. Kind of gruesome because, you know, these poor firemen that showed up to fight the fire after the explosion all had just horrible, horrible deaths because they got so massive doses of radiation. But I digress. All right. So all three of these types of energy are more energetic. They're on the high energy end. Radio waves, microwaves, infrared. Obviously, radio waves don't hurt us. I wouldn't want to cook myself in a microwave because it's pretty small, but what it's doing is exciting your water molecules. Infrared you can feel on your skin is heat, and then, of course, visible spectrum. And our visible spectrum, Roy G. Biv. We all know and love the rainbow. All right. Notice on this drawing that I have now written all over, this end, we have large wavelengths. This end, we have very, very small wavelengths. We already talked about this is the energetic end. Here, let me write wavelength. And that's the length of a wave from one crest to the next. And we'll write wavelength here. And we know that this end is high energy. So, as your wavelength gets smaller, you get more energetic. So you've got long wavelengths, and as they get smaller, they get more energetic. And stop and think, when you're waving, make sure my hand's in the picture. All right, here we go. When you're waving, this is a long wavelength. This is a short wavelength. In fact, this is a really good joke. Microwave. Get it? So, a long wavelength, you're not waving very frequently. So long wavelengths have low frequency. And short wavelengths have high frequency. High frequency, high energy, teeny tiny wavelength. Low frequency, low energy, big wavelength. All right. Here's the definition of wavelength from one crest to the next. Amplitude is how tall they are. We use the Greek letter lambda. It looks like an upside down Y, and I have fought kids for years on this because they're like, why can't we just use a W? Well, you could if you weren't in college chem, but you're in college chem, you need to use the right notation. So you just make this goofy little upside down Y. Sorry, that's not very neat. I should put this down better. Here we go. Better. Wavelength can be calculated if you know the speed of light. All right, the speed of light is light that is traveling at a rate of 300 million meters per second. Okay, 300 million meters per second. It takes 8 minutes for the light to get from the sun to the earth, and it's traveling 300 million meters per second. All right, the nice thing about wavelength, remember we looked at that chart and we saw that as the wavelength got shorter, the frequency went up. It's an inverse relationship. So, if you can see down here, I'll move my head a little bit. Wavelength and frequency are inverse. So if you can divide one by the other, you will come up or if you can multiply them by each other, you will come up with the speed of light. All right, so the speed of light, we use the letter C. The speed of light is equal to the wavelength times frequency. And frequency, you get to use this funky little v. Okay, that's on our next slide. Here's our frequency page. I can move my head back up. Frequency is the number of waves that pass a given point per second. So our units are really funky. Before, with wavelength, the units were in meters. Now we're talking frequency, they're in waves per second. Per second means you're dividing the number of waves by 1 second. That's also called a hertz. So you can either write it like this, you can write it hertz, or if we write it like this, if you stop and think about math, a -1 means it's 1/2, which is the same as that. All right? It's abbreviated by the Greek letter nu, which is this funky v. So frequency is equal to the speed of light divided by wavelength, and wavelength is equal to the speed of light divided by frequency. So let's practice. What is the wave? We can do math with this. It's very exciting. What is the wavelength of a wave that has frequency of 2.3 times 10 to the 14th per seconds, or hertz? Okay, well, our formula, C is equal to wavelength times frequency. What did I say the speed of light was? You don't have to memorize it. It'll always be given to you. It's a standard. Speed of light is equal to wavelength, that's what we're solving for, times frequency, 2.3 times 10 to the 14th, 1/seconds. Now, what do you do with math? I wonder if this will move. Let's see. We could take this and make it smaller so you can see it, maybe. No. I'll put a line between them. If we take 3 times 10 to the 8th meters, here, I'll write it up here. 3 times 10 to the 8th meters per second, and we divide it by 2.3 times 10 to the 14th, 1/seconds, that our seconds will cancel. That will give us meters, which is our unit of measurement for wavelength. So let's use a calculator and do that. So we're going to take 3, and this calculator, 3, and I'm going to use the exponent. Exponent's going to be times 10 to the 8th, and I'm going to divide that by, and I've forgotten 2.3 times, that's exponent to the 14th, and we get 1.3 up here in the corner, or you can read the whole thing, 1.30 times 10 to the -6th. .30 times 10 to the -6th meters. That's pretty small. Okay, so that's micrometers. That would be 1.3 micrometers. All right, what is the frequency of blue light that has a wavelength of 499 nanometers? So now we're going to go the other direction. First, we have to change nanometers to meters. 499 nanometers. We know that 1 meter is equal to 1 times 10 to the 9th nanometers. So we're going to get 499 times 10 to the -9th meters. We're solving for frequency. I'm going to use my eraser here and write this out up here. So frequency of blue light. We're solving for frequency, which is this guy, which means we're going to move this guy over here. Speed of light is equal to, or frequency is equal to the speed of light divided by wavelength. So speed of light 3.0 times 10 to the 8th meters per second divided by wavelength, which we said was 499 times 10 to the negative 9th meters. Our meters will cancel. Our answers are going to be 1 over second. 3 times 10 to the 8th exponent 8 divided by, and I've already forgotten what it was, $499 exponent negative 9th. And we get a really big number. I don't know if you can see here. Here's our number. 1,000 million billion trillion. 601 trillion waves per second. 601 trillion. If we write that in scientific notation, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, it would be 6 times 10 to the 14th meters per second. Not per meters per second, just per second, waves per second. All right, we haven't talked about energy yet, so we'll skip that one. Now we're going to talk about energy. Okay, remember our picture back here? And we said that energy was at the small end, small wavelength, high energy. That makes sense. You've got a short frequency. It takes a lot more energy than a long frequency. So that energy and frequency are directly related. And Max Planck is the scientist that came up with this. Okay? Max Planck realized that they were directly related, and he came up with a way to calculate that. All right, so let's talk about Max Planck. First of all, we have a horrible mistake on here. So, where it says 10 to the 8th, cross out 8. It's 10 to the negative 34th. Okay? We're talking about a conversion factor. When we get to moles, we'll do some stuff with conversion factors. But a conversion factor is how, if you want to go from inches to centimeters, you have to multiply the number of inches you have times 2.54 centimeters in 1 inch. If you want to go kilograms to pounds, there are 2.2 kilograms in 1 pound. So it's a conversion factor. Planck figured out that the energy that light had, they called it a photon because he saw it as a particle, the energy that light had that was given off by an electron moving was directly proportional to the frequency. And that makes sense. The faster you wave, the higher the energy, right? So if he knew the frequency of something, and we just calculated frequency of that blue light, frequency is 1 over seconds, all he had to do is multiply it by his conversion factor to get energy. And the conversion factor is 6.63, I'm going to shorten it a little bit, times 10 to the negative 34th joule seconds. Seconds cancels, we get joules. Joules is energy. If you think back to when you did heat in Gen Chem or Honors Chem, heat was in joules. Joules is energy. You may have done that in physics too. All right. So let's go back. Well, we don't have to go back. This is the problem that we just saw on the other slide. If we pull we had 6 times 10 to the 14th, multiply that by 6.63 times 10 to the negative 34th, and we come up with a teeny tiny number. Why isn't this in scientific notation? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 3.98 times 10 to the 19th. Joules. All right. Of course, you can pause anytime that you need to take a break. So, Max Planck proposed that the light was moving as a particle. We call that particle a photon. These notes say that they're in energy packets. We call it a photon. Bohr, in the meantime, is looking at electrons and declares that electrons move like planets around the nucleus, being the sun. And he studied hydrogen and was able to learn a little bit about what the electrons do. Okay? Electromagnetic energy is released in discrete energy packets in a quantized form. We call it a quantum of energy. And as the electrons, it should say electrons, move between energy levels, they require that quanta of energy to do that moving. I'm going to stop here so that we don't have a hideously long video.